Hello there. Let's see a new example of problem where we are going to need to integrate Newton's second law. Imagine we're in a weird planet where gravity is not constant, but it depends on time. G is equal to minus beta t. Well, more than a planet, this could be a spaceship that is accelerating with increasing acceleration. Okay, assuming it's a dream planet. What is the angle at which you need to launch a ball to reach the furthest distance? Well, we have already solved a similar problem with Earth's gravity in a previous video. Let me write the equation of motion, Newton's second law. In the x-axis, nothing is different from Earth. There is no acceleration on x, so the object will move with constant velocity, uniform motion. On the y-axis, though, we have that the acceleration y 2 dots is equals to minus beta t. I integrate this expression once and get the velocity as a function of time. I integrate it again and find the position, the height as a function of time. In order to maximize the range volta x, I derive it with respect to the angle and equal it to 0. To find the range, I impose that delta y is 0. This gives me 2 times. T equals to 0 is the launching time, and t equals to a square root of 6 v naught sine of theta over 6 is the landing time. I substitute this time in the delta x equation. Now, in order to maximize the range, delta x, I derive it with respect to the angle and equal it to 0. Some wibbly wobbly timey math stuff, and tangent of theta is 1 over square root of 2, so theta is 35.26 degrees. If we plot the range of the object versus the angle, we see that it has a maximum right at those 35.26 degrees. So this was another example of problem where we need to integrate Newton's second law to find the equation of motion and describe this motion. Remember that you've been doing this your whole life, but all the problems that you solve, they consider constant acceleration, so you learned the solution and applied it without needing to integrate it every time. That was a very special case, though, very important, because that's what gravity does. But just a particular case, in that case you had that parabolic motion. Now, if we plot the y position versus the x position, we get this plot. This is not a parabolic motion anymore. This is not normal gravity anymore. May the science be with you.